let me start. I hope it will. I hope slides will appear. I would like to make a few disclosures. The talk which I'm going to make is full of formulas, and it's my apology. It's a specialized talk. Not that I would like to make talks like that, but I would rather prefer to do it for more general audience, but this is only what I have. It's a kind of my nature and the nature of the subject. So my apology, too many formulas. Yes, please. Sure. Okay. Yes. Okay. But before the talk starts, I just would like to make some short comment about my personal history and how I came up. It's already here. It may be working. Yeah. Yes. A few words about my personal history, how I came up with this problem. Of course, I was very familiar about its existence, but there are many problems afterwards. But in late, sorry. How does it work? Yeah. That's the next slide, right?
No, next slide. Or one of those and try to avoid the joystick.
Okay. So in late 90s, in the beginning of penetration of topological ideas of topology in condensed matter physics, I asked myself a question. Suppose I have a two-dimensional electrons in two dimensions. It was a time of cuprates, and that was a layer material. And then I would apply magnetic field and ask what happened with the energy of electrons. Does the energy rise when magnetic field rise, or perhaps decrease? What happened? What happened to the energy? So magnetic field localized electrons. They start to rotate along some small orbits, which generally decrease its kinetic energy. So energy is supposed to go up. And that is the subject of Landau magnetism. So energy in magnetic field a little bit larger than energy of electrons without magnetic field by diamagnetic susceptibility can be computed. It's textbook's result. So energy goes up, electrons localized, and rotating, their kinetic energy rise. But then there is another effect that these orbits occupy, if they occupy the whole plane and there is no space, they also can gain in sort of exchange energy, because they're kind of getting more frozen. And indeed, some simple computations showed that if magnetic field not small, but large, such that magnetic flux is integer times number of electrons, which means that certain number of Landau levels of field, the energy simply doesn't depend on magnetic field. Without magnetic field, an electron has the same energy as in magnetic field, provided that levels are filled. 1 level, 2 level, 3 level. The energy is the same. It's fixed by this number. This result was for free electrons. And clearly that interaction or a lattice will break this degeneracy. And that's in next year, in the paper with Maurice Rice and Paul Lederer, we showed that if we put electrons on a lattice in magnetic field, and this is a Hofstadter problem, the energy actually goes down. So electrons like magnetic fields. And if there is a mechanism for magnetic fields spontaneously generated, the energy would prefer that. That brought me, yes, so electrons, magnetic field is good for electrons. So they like to be in magnetic field, the energy is lower. Okay, that brought me to the problem of Bloch electrons in magnetic field. So electrons now sitting on a lattice. Magnetic field is up. Flux phi per unit cell tells me how big is magnetic field. And electrons can jump, it's free particles, can jump from lattice from side to side. This is the tight binding Hamiltonian. And coupling, hopping amplitude T is just a phase proportional to the such that if you go around plaquette, there is a flux phi through plaquette. I will later use notation for this flux is q squared. Okay. That's one of the textbook problem. And it can be reformulated in terms of magnetic translations if operator T, which translates electron in direction n, this way, and this in direction m, then these operators commute by obeys this Heisenberg algebra. It's called Heisenberg algebra, where Q is a flux. And in terms of magnetic translations, the Hamiltonian is written by this simple form. So it's a translation up, down, sorry, left, right, up, down. Okay, that's a problem. So what we want, yeah, that's a problem. Magnetic translation can be realized in many different ways, and this is one of the representations, which is called Landau gauge. In this representation, translation along x-axis is simply translation, but it's simply shift, but translation along y-axis is multiplication. That's a representation of the electrons. As a result, the Schrödinger equation for electrons on magnetic field becomes one-dimensional equation when wave function psi, particle with wave function psi hops from side n to the right, to the left, and when they go up and down, they acquire a potential, periodic potential. K is a momentum of the plane wave, and phi is a flux. Okay. In this form, this equation is known in mathematics and physics without relation to two-dimensional Bloch electrons, but just as equation. It's a discrete equation in periodic potential. Would this discrete operator will be replaced by differential operator that will be Mathieu equation, and in this form it's called almost Mathieu equation or Harper equation. It's also described quasi-crystals, has tons of applications, and one of the standard equations in spectral theory. Okay. That's one of the celebrated models of spectral theory. Tons of applications, chaos, quantum Hall effect, etc. Okay. Now, if the flux is rational, the flux per unit cell is a ratio of two numbers, so it's a rational number, P and Q. The spectrum consists of, it's a periodic, it's a Schrödinger equation, periodic potential. The spectrum will consist of Q bands. And the Q is denominator, so number of bands and number of gaps is not sensitive to the flux, but is sensitive to denominator. This is how arithmetics or number theory comes to the play. So if you change flux very little, but such that denominator change dramatically, maybe small change of the flux, completely rearrange the spectrum. And that's a colorful picture which describes the energy which rises in this axis versus magnetic field. So you can see that if you move along, if you change magnetic field, change the flux, the spectrum rearrange very drastically. Okay, this is how number theories comes to a play, and that substance is neither, if P and Q are very large and flux is, say, irrational number, that it will be infinitely many bands, infinitely many gaps, distance between will be arbitrarily small. As Doug said, they form a counter set, but it's not just a counter set, simple counter set. It's called singular continuum. It's a very special counter set on which mankind knows very little, and it appears naturally in such simple equation, which has so many applications. The spectrum is a singular continuum counter set. We know little about it. We knew little about it. We still know little about it, but it's all over the places. So if it is phi is irrational number, say square root of 5, then it's not a metal, it's not an insulator, it's something in between, because many gaps, many bands, everything very small, arbitrary. So what is physical property of this substance? What is its specific heat? What is its transport coefficients? Unknown, and still unknown. Okay. So this is an incomplete list of work before 1990s. So as far as I understand, it starts from Zach and Asbel's seminal work in 1964, who actually realized essence of that arithmetic is essential here, but it's mostly they describe the story. Then Doug's work in 76, there's 1 year, very important work Fabre and Rand, 80s, Avron, 85, mathematicians, Belisard and Simons, 80 to 90. Very important work which explain quantization of Hall conductance by Thouless and Mohita Komoto, Sainz Wilkinson, etc. Okay. Yes. So it was empirical observation of Hofstadter, but also in Asbel before, that the spectrum is not really erratic, but quite ordered. But that was kind of aesthetic words, so we don't know really what means ordered. The butterfly looks very nicely, it's very appealing, suggestive, but what is really description of this butterfly, it remains unknown. So in 1994, together with Anton Zaborodin, we have shown that the problem is in fact integrable and solved it by Bethe Ansatz, and this is the subject of the talk. I briefly describe the story. But since every time a butterfly appears on the screen, people start to talk about aesthetics, and my comment to that problems which aesthetically appealing, they also analytically appealing. They have deep analytical structure, not just beautiful picture, but there is something behind this, and if we can have tool available to study it analytically, some analytic beauty also must be there. It may be difficult to uncover it, but it's sort of hidden there. That is a kind of philosophy which I had in all my career. If something looks beautiful, it must have some interesting analytical structure. And indeed, Hofstadter problem is integrable, and I will try to explain what it means in a few moments. After that work, there was a very important work of Mohita Komoto and Yoshihiro Hatsugai and Kensei Fujikawa, which extends this solution. Bethe Ansatz solution in almost in the same year, Fadeev and Kashaev generalized solution for entire spectrum. We consider it only middle of the band. And finally, in 97, together with Alexander Abanov and Job Telstra, we determined hierarchical structure of the spectrum. I will say a few words about it. After that, I didn't touch the problem. It becomes, it hits the wall and it becomes really complicated. And I decided that maybe it's time to wait before mathematicians or next generation will adapt what we did. It's still not happened to that time. Okay, so that's my talk begins. I would like to explain what does it mean that Hofstadter problem is integrable. So that's equation. We want to solve that equation. That's it, period. Computer can do this. If flux is rational with denominator of 17, this is basically diagonalization of 17 by 17 matrix, depending on how big of the flux. But we are not interested denominator, but we are not interested to this. We are interested when denominator is large, numerator is large, and flux, say, square root of 2. Then what happens there? But if Q is finite, P is finite, it's just diagonalization of Q by Q matrix, period. Right? Okay. If not, it's okay. Now, as I said, it's a relative of Massieu equation. Massieu equation, it's a differential equation with this, when here's a second derivative, Schrödinger equation in periodic potential, standard thing. And there is very little about Massieu equation. Very little known about Massieu equation. Very little. And that's a discrete version, so it must be even less known. It is even less known. Nevertheless, it has the problem, this equation, it's a finite difference equation, can be algebra, its spectrum is algebraic, and let me explain what it means. Here I summarize the part of the story in this short slide. First notation, so this flux is, e to the flux is Q. Q is a P of Q, flux is a rational number, P divided by Q. Then the claim is that the energy of every band, basically this beautiful picture, is sum of Q numbers, complex numbers. Energy is real, but it's sum of complex numbers, Q. And these numbers are roots of the Bethe Ansatz equation. That means they are solution of that algebraic equation. So instead of solving differential equation or this difference equation, its solution, its spectrum given by sum of numbers z, which we called roots, which obey algebraic equations. So if you give me Q and P, that equation, computer can solve it too, find these numbers, plug in that energy. Having this energy, we can draw the picture, the butterfly picture. It's and that means integrability, that the spectrum is given by finite algebraic equation written in a very close form. Maybe it's difficult to solve this equation. Maybe to solve this equation even more difficult than to solve the original equation. It's not true, actually. It's easier, but the equivalent, this equivalent to that, and that's subject of integrability. And it's happened very rare. If you change this equation a little bit, it's all ruined. It's very, very specific property of very, very fine-tuned equation. So we touch this equation, it's produced butterfly. Butterfly is beautiful. It has some inner structure. And inner structure is hidden in the fact that the spectrum is algebraized. I'm not sure how much you can appreciate this message, but yeah, that's from here to here. Okay. So once we have these roots, we also can construct the wave function. Not only the energy, but it's the wave function, which is a bit more complicated than energy. And the construction is the following. Have these roots, you construct a polynomial as a function of z, complex variable. It's a polynomial with this root. And then take this polynomial at points z located on a circle, sum it with very specific coefficients, which are called dilogarithm, quantum dilogarithm, and that will be the wave function. Okay. So people who are familiar with Bethe Ansatz equation may recognize that that equation is very similar to the solution of the Heisenberg chain. But in this case, Heisenberg chain is only on two sides, but on every side there is this large spin, which equal to the number of bands. So there is some analog between Hofstadter problem and solution of the Heisenberg chain, magnetic chain. Okay. So now we will produce this picture, not from original problem, but from Bethe Ansatz equation. Solve it, find these numbers, compute the energy, plot. Okay. Now, I would like to discuss, spend a few moments how to obtain this equation. And actually, I don't control the time. Can you remind me when I started? And
started at 10 past.
Sorry?
10 past. So it's about 8 minutes left.
8 minutes. Yeah, I have to. Then I have to speed up. Yes. Okay. I have to a little bit speed up. I say just a few words how to obtain this equation. And yeah, I would bring up the analog. Let's consider, instead of finite difference equation, a differential equation. And then we know that some differential equation has solutions which are polynomials. For example, hypergeometric equation. Some equation with coefficient A and B and C chosen properly, the solutions are polynomial. Why it happens? It happens because this operator actually represents a rotator. If there is a spin, and spin is a matrix, some matrix, then we can write the Heisenberg Hamiltonian for the spin and use the representation that spin J can be represented by differential equations, then this matrix also equivalent to these differential operators. This matrix has finite number of solutions. That operator has a finite its solution with polynomials, and the roots of these polynomials correspond to the energy of the rotator. And the analog of that for discrete equation invoke generalization of rotational group SL2 to so-called quantum version of rotational group SL2. I don't have time to describe it, but would like to say that if you write an arbitrary general form of equation, general form of difference equation of the second order with some unknown coefficients A, D, V, and ask, show me A, D, and V such that solution could be written in terms of polynomials, and then I can do this by by finding a representation of quantum version of rotational group, and this quantization parameter Q is the flux. So quantum version of rotational group, that's a rotational group, but it's quantum version. I don't have time and intention to describe all this, but there is such a concept, and one spin can be represented by matrices. The quantum version also represented by matrices, and if and that representation determines this A, D, V. So we can classify all equations which has this interesting algebraic spectrum. And Hofstadter equation happened to be in this class. It's very, very tiny class, but it happened to be in this class. So once, sorry. Okay. Yes. The motion of electrons in magnetic field along a lattice can be represented through operators of quantum group. So B and C, it's analog of S plus and S minus, and that's relation between B and C and magnetic translations. Once that has been noticed, one can use representation of the quantum group to write this Bethe Ansatz solution. It's a little bit technical, I understand, but I would like to emphasize that it could not happen. It happened by kind of a pure accident, and to find it, there is no guarantee that it happened, and we found it, but we first have a belief that something nice must happen, and it's indeed happened. So once you have a belief, this belief can drive you to a pretty simple formula, and that solution. Okay. Now the question now is, once we have it, that's surprising, but we already have it. So the question, how we utilize it, and can we solve these algebraic equations? They're pretty complicated. But apparently, and it's very difficult to solve them if Q is finite. If it is 1, 2, 3, 4, 5 zones, I can do it by hands. If it is 15 bands, I can do it by hand, but computer can do this if it's 1,000 bands, and I am interested in infinite. Computer cannot do this anymore. But that's where the problem is. But once Q is is very large, then a new feature appears within these equations already. Its solutions, that is one of the solutions. So of every point is this Z, and solution written for denominator 55 and denominator 34. The fraction is, the flux is 34 by 55. So there is a 55 bands and 54 gaps. And therefore, this solution, this equation must have 55 roots, and they are drawn here. And they are organized. They are not just random. If there are many, they start to organize in the form of so-called string. String is characterized by center. It's a set of numbers located on a unit circle equidistantly, has its length, how many of them, they equidistantly located, and has a center. So you can see that it's maybe requires some time to understand what is here, but that picture consists of 2 of string of length 1, 2 string of length 5, 2 string of length 21, and okay, they have the structure. They have the structure. So instead of find all of these 55 roots, we have to find centers of the string, because the rest is, it's an approximate formula, but becomes exact when Q is large. Right? So instead of 55 numbers from here, we have to find what? 1, 2, 3 numbers only. Once we find 3 numbers, I can draw this picture. Okay. The next observation is the maximum, the largest string. The largest string is string 21 in this example, which has 21 participants, elements. This 21 happened to be the whole conductance of the band we consider. The whole conductance is topological characterization of the band. It's number which I can compute without solving equations. You give me P over Q, I can compute whole conductance. And that tells me how many, what's the largest string, right? So instead of solving this equation, I rather compute whole conductance from entirely different means. And I know that this equation possesses the largest string 21 because its whole conductance 21. Out of 55 points, I can draw 21 points immediately. It's the next surprise. There are tons of, all these steps which I'm describing are surprises. Okay. Then what we have next noticed that if I take the largest string from here, 21, remove these points, it will be much less. And then what remains will be a solution, better solution of the same equation, but for a different flux. And that's brought so-called hierarchical hypothesis. I described this hierarchical tree hypothesis. I describe it here. So each solution is labeled by content of strings. The length of the longest string is given by of a given band given by whole conductance of the band, which computed independently. And then when you remove the string, we come to a different problem which describe a different flux. That's produced a relation between problem with one flux to the problem with a different flux parent produce daughter by adding this higher order, the largest string, whose length is whole conductance. And that's a hierarchy. Having that equation, which approximately true, actually it's not exact equation, not exact recursion, but becomes approximate, but becomes more and more exact as number of bands grows. When denominator is large, numerator is large, when they go larger, that relation becomes more and more exact. And that's a small illustration. So we start from the problem which I can have solved by hand. Then I know how to change the flux such that one more string appears, and then one more string appears, and so on. And that's already very difficult, but I can predict their position. If I start to solve original equation, it's almost impossible. But knowing this hierarchical tree, I can predict the position. And that's example for Fibonacci for golden mean. For golden mean, if the flux is square root over 5 minus 1 over 2, golden mean, that number can be approximated by Fibonacci sequence. And from this Fibonacci sequence, I compute whole conductances, compute this position of the string, make a product of them, approximate wave function. Wave function is not exact if I stop here, but if I continue, it becomes exact, asymptotically exact. And so this idea provides a so-called hierarchical tree. It's pretty complicated, but that's one of the examples for this example of approximation of 33 divided by 55. That's a sequence of rational number which converge to the number I wanted. Number of bands grow, but they kind of, this is a parent, and this is daughters, and daughters know parents and can be constructed of the structure of parents, and the population grows and grows, and this is how butterfly is structured. And that's what we can predict. So when we look for this picture, as I said, it looks nice, but what can we say about it really? And here what we can say, that among this picture, there are interesting passes. So you start from one point here, and then there is I can provide a guiding book, a guided tour among this complicated structure. I don't expect that it's clear how it has been done, but it's what I would like to emphasize, that within this sort of appealing picture, there is a structure, there is a guided tour. When you move along generation of these bands, and the number increase, population increase and increase, but we know the DNA, right? We know the DNA analysis. If you give me this band, I can tell you, I can follow its tree to the pra-parents from the origin, right? So they come from the one parent, but now it's a whole generation, but I know the DNA, right? So it's not well understood and well studied, but there is an algorithm, and we can provide a guided tour in this one. Why guided tour is necessary? Because the distance between the width of the parent band and the daughter band next generations, they changed by power of denominator to some power. And the proof is, the point is that if we're going along this tree, then bands are then width of the bands converges. If you don't go along this tree, say jump from here to here to here, that will be random numbers. They don't converge. If you go along this tree, they converge to some power law, right? And eventually, each band characterized by its anomaly dimensions. And once we find this anomalous dimension, then we know everything about the spectrum, about this butterfly. It's all consistent, these numbers. If I have them, I can compute specific heat, transport coefficients, conductivity, optical conductivity, whatever. It's all sitting in these numbers. To get these numbers, we first must identify passes where convergence goes to these numbers, and that's what has been done, and then find these numbers. And unfortunately, this is where the science, the progress stopped. Let me repeat. Once we know the dimensions, this anomalous dimension, we know all physics. Physics is singular continuum, but it's characterized by infinite set of anomalous dimensions. But the main problem, whether we can find them, and it's remain unsolved. So we identify the passes where the sequence converges, but what is converging to unknown, remains unknown. Okay. And so let me, in the spirit of this conference and Doug's talk, let me conclude by a little bit clumsy English translation of a short poem of Nabokov from his gift in chapter 4. It's originally in Russian, but there is a translation in English. Well, it's short. The truth bends her head to fingers, curves cupwise. So the truth turn her back to us and have something in her fingers. And with a smile and care, examines something she is holding there, concealed by her own shoulders from our eyes. So the truth exists, but it's hidden from our eyes because the truth turns its back to us. But it's important to know that it has something in her hands. It's our task to find it. It's hidden, but it exists. Thank you.
Yeah, thanks a lot, Paul, for illuminating this Harper problem now from this mathematical physics perspective. Any questions, Theo?
Well, the fact that the Harper model corresponds to integrable systems is kind of trivial because it's a single band approximation, single band system if you wish, and in one dimension this is always integrable because I mean you have the energy as a conserved quantity, so this is the integral of motion and thing is integrable. Now, if you want to find the Hofstadter butterfly, as Doug already pointed out, realistically in a physical system, you have to use a superlattice.
You have to use what?
A superlattice. I mean, either you need extremely high magnetic fields to get of the order of one flux quantum within one unit cell. So you cannot achieve these high magnetic fields. The other option is to increase the size of the area of the of your system, of your crystal. That is to use a superlattice. This is what we will hear later today, I think. So a lateral surface superlattice has a larger area, so you need much smaller magnetic fields to observe the butterfly. But then you get close to the classical limit, and it will not be sufficient to study a single band approximation because the classical limit is chaotic and not integrable. And then you need to study many Harper bands that start mixing. And that's what we did. A student of mine, Gerhard Petschel, who died unfortunately quite some time ago. So in 1993, we published a paper in Physical Review Letters where we considered the mixing of arbitrarily many Landau bands, Hofstadter butterflies, if you wish, using the eigenfunctions of the b to the infinity limit that Alexander Rao introduced. And this gave us a generalization of the Harper equation in matrix form. So you have a vector and the potential becomes a matrix. And we solved this with a matrix continued fraction expansion. And it leads to effects that you can get transitions from absolutely continuous to singular continuous spectrum and so on.
Okay, I think this was a comment which was perfectly now moving on to the next talk, because you talked about already now the superlattices, and I think this gives the opportunity now for Dieter Weiss that we will have the next talk on experimental realizations now, and to
maybe I should provide.
I consider it as a comment, but maybe
it's just a short comment. You know, there are a subset of people in the world who worked in integrable systems. If you ask what's the definition of integrability, the definition is it's a set of people who work on integrable systems. So there is no good definition of integrability. But being an expert, I can assure you that the simple quantum mechanics could be integrable. It's 1 degree of freedom, one particle, could be integrable or not integrable. And in that particular case, application of the standard concept about conservation laws is not really applicable. There is a deeper definition of integrability. So these simple equations, Harper equations, one of them, could be integrable or not integrable, depending on the potential. And that happened to be integrable, which means that this equation has much deeper hidden symmetry that you can see it by naked eye. And the symmetry is not expressed in terms of just conservation laws.
Calling this separable and non-separable.
The right word for that is algebraization of the spectrum. It's called algebraization of the spectrum, but I don't want to come to the details. For integrability practitioners, that is integrable. If you change the equation a little bit, it stops to be integrable. But maybe I can say one more thing. So that equation is related to, as any linear equation, related to dynamical systems. Dynamical system is non-linear equations, but they're equivalent in some sense. There is a transformation from one to another. That one is related to so-called kicked rotator. It's a rotator, and sometimes you kick it periodically, right? It's a dynamical system, non-linear equation, and there is some mathematical correspondence between this kicked rotator and Harper equation. Now the question about integrability can be formulated in the following way. Is kicked rotator chaotic or not? Does it move along tori or it's chaotic? The answer is it's not chaotic. And you can see it by naked eye looking for these equations unless you understand the relation to this quantum group symmetry and discover that aspect. But
maybe we should, I think, thanks for this comment. I think this was important. You can discuss this later on after the next talk in the coffee break, but now we turn indeed to the question whether one can experimentally see the butterfly, change gears, and Dieter Weiss will give now the next talk.